Hey everyone, and welcome. We're practically swimming in data these days, but how do we find the real story hiding in all those numbers? Today we're going to become data detectives. We're diving into descriptive biostatistics, which is just a fancy way of saying we're learning the tools to solve some seriously important health mysteries.
So picture this. A brand new factory opens up in a small town. Great news for the economy, right? But then doctors start noticing more and more people getting sick with a rare illness. So what's going on? Is it just some awful coincidence? Or is that factory the real culprit? How in the world do you find the truth?
And that, right there, is where biostatistics comes in. It is literally the science of being a data detective for public health. It gives us the methods we need to take a puzzle like this, look at the raw numbers, and turn them into answers that can actually save lives. Okay, so here's our game plan for today. We're going to start by getting into the mindset of these health data detectives. Then, we'll get into the fundamental clues of any investigation: populations, samples, and variables. After that, we'll see how to make the data tell its story, how to measure health and risk, and finally, we'll look at the incredible impact this work has in the real world.
All right, first up, let's put on our detective hats. This whole section is about the why. Why do we need a careful, scientific way to turn a whole mess of numbers into clear answers we can actually use? It's the foundation for everything that follows.
So, as any good detective knows, you have to start with the basics. That brings us to our fundamental clues: populations, samples, and variables. You've got to know exactly who and what you're looking at before you can even think about solving the case. First things first, we've got to know who we're talking about. The population is the whole shebang, the entire group we're interested in. So in our mystery, it's every single resident of that town. But, trying to study every single person, that's usually impossible. So, what do? We take a sample, a smaller, manageable piece of that population that, hopefully, represents the whole group.
Next up, what kind of information, what clues are we collecting? Well, one type is a categorical variable. This is data that fits neatly into boxes or categories. Think of it like a checklist. Are they a smoker or a non-smoker? Are they sick or are they healthy? It's one or the other.
And on the flip side of that, we have the continuous variable. This isn't a simple category. This is something you can measure on a sliding scale. Things like a person's age, their exact weight, or their blood pressure reading. It can be a whole range of numbers.
Okay, let's put this all together for our factory town problem. Step 1, what's the population? Easy, all the town residents. Step 2, what's our sample? Let's say we randomly select 100 residents to study. And step 3, what are the variables we're measuring? We'll track their age, that's continuous, and their sickness status, which is categorical. Boom. Just like that, our investigation is off to a solid start. So, we've gathered our clues from the field. Now what? Well, this is the exciting part. It's time for telling the data's story. This is where we take all that raw information and start looking for the hidden patterns, the trends, the secrets hiding inside the numbers.
And to do that, we have three classic go-to tools. You've probably heard of them. The mean, which is just the good old average, the median, which is the number smack dab in the middle of our data, and the mode, which is simply the value that shows up most often.
Now, you've got to pay close attention to this because it's absolutely crucial. It's called the outlier effect. An outlier is just a really extreme data point. So look what happens here. When we add just one person with a ridiculously high salary, the mean, the average, gets yanked way up. It's totally misleading now. But look at the median, the middle value. It barely moves. It stays stable and tells a much more honest story. That's why the median is often our most trusted guide when the data gets a little wild.
Okay, so here's the thing. Our ultimate quest is to discover the truth about the entire population, right? But we can't. We can't talk to everyone. So in the world of statistics, we have special symbols for these true, perfect values we're hunting for. The true average of the whole population is called mu, and the true measure of how spread out the data is called sigma. Think of these as the population's secret parameters, the hidden treasure we're trying to find.
But since we can't get to that hidden treasure directly, we have to work with what we've got, our sample. The numbers we calculate from our sample are called statistics, and they're our best guess. So the average of our sample is called x bar, and its spread is called S. We use these real-world numbers from our sample to try and estimate those true hidden parameters of the entire population.
And that term, standard deviation, is so important. Along with variance, it's our #1 tool for understanding the spread of our data. A really small standard deviation means all our data points are nice and cozy, clustered together. A big one means the data is all over the place. It's a single number that tells us if our data is consistent and predictable or totally chaotic. All right, we've got our descriptive toolkit ready. Now it's time to put it to work on the big questions. In this next part, we're measuring health and risk. This is where we really get to the heart of public health, putting numbers on disease and figuring out just how big a danger really is. This slide breaks down two of the most important ideas in this field, and the analogy is perfect. Think of prevalence as a snapshot in time. It answers the question, how many people in this town have the illness right now? Incidence, on the other hand, is like a video. It tracks the story over time and answers, what's the rate of new people getting sick? One's a photo, the other's a movie. Now, a really smart way to measure incidence is with something called person time. In a study, some people might be followed for 5 years, others for only 1. Person time accounts for that. You just add up the total time everyone was observed, we call that person years. Then you count up the new cases of illness and you divide. It gives you a super precise rate of how quickly the disease is spreading.
So how do we actually compare risk between, say, the factory workers and everyone else? Well, the tool you use depends on your study. If you're doing a cohort study, following people forward in time, you use relative risk. It basically asks, are the exposed people 2 times more likely or maybe 5 times more likely to get sick? But if you do a case control study, where you start with sick people and look back, you use the odds ratio. That asks a different question. What were the odds that the sick people were exposed compared to the healthy people? It's all about picking the right tool for the job.
And there are a couple of other really useful measures. The risk difference tells us, in plain terms, how much extra risk the factory adds. And population attributable risk, well, that one's huge for public health officials. It helps them estimate how much of the illness in the entire town could potentially be wiped out if the exposure from that factory was gone.
So, we have built this incredible toolkit. We know how to describe data, find patterns, and measure risk. Now for the final and most important part, the biostatistician's impact. This is where we see how all this theory gets turned into real-world decisions that affect all of us.
See, a biostatistician isn't just someone crunching numbers in a back room. They are central to public health. They design studies to be fair and unbiased from the start. They analyze incredibly complex data to find the real signals. And maybe most importantly, they translate what they find into plain language for doctors and policymakers so that their work can actually inform policy that saves lives.
And that brings us right back to our factory town. This is the whole point. Biostatistics gives us the evidence we need to turn a suspicion, a fear, an educated guess into certainty. And once you have certainty, you can take action, whether that's putting in new safety regulations at the factory or giving the community the peace of mind that there's no connection at all. We've seen just how powerful these tools are for reading the stories hidden inside our health data. So I'll just leave you with this final thought to chew on. What story is all the data in the world around you trying to tell?